And the last thing that I need to do, I should have done this first, is I need to get my little stylus. Stylus, love my stylus. Have I told you that I love my stylus? So let's talk about this. So I'm gonna, before I go too far into this, I'm gonna go back into the little drawing pad over here. And I'm going to introduce a notion for you guys. I'm just gonna start drawing. And let's say you have something that sits on the outside that's known as your GPA, some big old-fashioned sum, right? We've got some thing. And the thing that goes into the GPA is the weighted sum of course 1 and course 0 and course 1. And let's say you take 2 and course 2 over here. Like, let's say you have 3 courses that your GPA is the weighted sum of these 3 things over here, right? And within these individual courses, you have lots of individual inputs of assignments, and each individual assignment has their own weight to this collective sum that is your GPA. This should look a little bit familiar, like a neural network, perhaps, yes? So where this differs, I think, between a neural network and what we have over here is that in a neural network, all of these other things are connected. Each individual score is connected to each other individual node over here. And in a sense, we can treat this exactly the same way, just arguing that all of these nodes, which I'm going to control Z out right over here, are actually weighted at 0, right? They're actually weighted at 0, but they're, for extensible theoretical terms, they're actually still present, okay? So in a completely unweighted system, let's say that in a completely uncurved system, there's none of these grades have any curves to them. In theory, we can look at any individual assignment and evaluate how that individual assignment has some direct influence on this output of this course grade right here. Right? I can say that this assignment has some weight, and that's going to go to this guy right here. And this assignment has that weight. And you can predictably understand the scaling of each of these things. And let's say your GPA is not computed based off of like 4s and 3s, some scaling transform function over here. Let's say we've got some abstract system that just uses straight up numbers, like your final average of everything, where we just straight up average all of these things together. In theory, in a purely linear system, you guys already know how to do this. How does this influence my GPA? How does this influence the grade of the course? You know that they're all kind of weighted the same and whatever. And you could predictably trace back individual parts, right? So if this were not like a GPA over here, let's say that this is some big weighted, your overall weighted average. So it's not GPA. I'm going to call it your not GPA. In your not GPA, which is your weighted average across everything, I would be able to intuitively say, well, I can change this score by this much, and that will change this score by this much, which will change this score by this much. And I can change this score by this much, will change that by that. And our brains are really good at doing that, right? Or at least being intuitive about it. Where it's hard is where there are nonlinearities, right? So if one grade is curved, if any of these things become nonlinear, then it becomes a little bit less intuitive how you would actually deal with this thing. So if this grade over here, if there's a curve on this one, right? If this has a weight which does some sort of weighted projection over inside of here, the answer to how much this grade influences your overall not GPA is suddenly not that nice linear formula. Because, well, I guess it is in a certain sense, but like at least at this node, how much influence this guy has. I'm goofing this up. The nonlinearities cause problems, right? Like nonlinearities, when this goes through a nonlinear function, how much influence this nonlinearly weighted assignment has on the overall influence is whatever. This, we still know we have some number over here. As long as this stuff is all linear, that's totally fine. And what I'm basically talking about here is the weight of this thing is the amount that your GPA changes with respect to an individual grade, right? So I could even say this is D GPA with respect to D, I don't know, assignment 2.3.1, right? You can figure out what that actually is. And the way to figure out the way that not GPA changes with respect to this is actually to propagate backwards all of the individual scaling factors. And that scaling factor, though, that scaling factor is not really just a scaling factor. That scaling factor is something more. That scaling factor is actually the derivative. That scaling factor is actually the derivative. We know it's one, but intuitively, it's that weight, but you know, there's a derivative in there. It's a calculus problem. This is going to get really, really nasty when we introduce all of these things to be nonlinear functions. But the simple reality is that the way of finding out the influence of any individual thing on the way all the way through can be determined by propagating backwards this influence of change, the way that a change here influences this, and a way that a change here influences this, and that a change here influences this guy. And that if I know the way to figure out his change is to propagate it backwards, how much will twiddling this grade over here, how much will a buyback of this many points influence the output of this guy? Well, I find that out by finding out how much changing this input changes that output, and how much changing this input changes that output, and how much that's the answer. Okay. And the mechanism for getting there is something that's known as the partial derivative, the weight of that individual assignment in the direction of that output. And so each of these planes, right? So if this individual class over here, and let's say they don't do the best job with it, but in this class over here, there is some assignment 0 and there's assignment 1. There are two things that can sort of change. Okay, I've got assignment 0 and assignment 1 over here. There are two things that I could change in this particular class. Let's just remove all this other. No, let's not. There are two things that could change, that could influence the way that assignment 0. Let's go back. I don't like my example. Sorry, I'm ad-libbing. My apologies. Let's say that this teacher is like actually bad, and they have assignment 0. They call it grade in the grade book, right? They have grade, and everything is just one big assignment. It's grade. There are two things that we could change to make the way that you score on grade, to make the output of this class different. I could change the weighting of like grade, and I could change the score I get on grade. Does that make sense? Like there are two dimensions. I can change, and so you would want to know if I change my score on grade, presumably that has some influence on output. And if I change the weighting of grade, that also has some output. These are two different dimensions. And I can look at the slope, how that output changes with respect to either one of these things, right? It's planar in the sense. And this is a linear function at this point, right? Now, if it were like curve, we would still basically do that same kind of thing. We would say, okay, well, how is this changing with respect to my individual weighting function? And how is it changing as opposed to the actual score that they get? There's still two dimensions over here, even if this is rounded input. I have choice A and choice B. And this is what a partial derivative is, right? We're used to taking dy dx, and I don't know how many of you guys are in multi. Presumably you've had some. Have you done derivatives? Have we done derivatives? Right? We like to take the derivative of x, right? Dy dx. But it's equally possible to say, well, we don't necessarily care about the dy dx. Maybe we care about dx dy. Maybe we care about the other dimension, right? And so in this world of partial derivatives, what we're going to be doing is we're actually kind of beginning to care about these other dimensions. So when we have this data that we're pumping into these systems, we're kind of exercising this notion that we don't really have control over the input. We're given the input. What we want to change is that other thing. We want to change the weights. We're going to be looking to change the derivative of the weights, not necessarily the change of the inputs in many of these cases. And we're very used to looking at derivatives over here, where we're like, oh, dy, it's the dy with respect to x. But in our cases right now, we're going to be kind of saying, to tune this network, how is it that other function, how is it that other element that changes the way this whole thing is going to output? So the big thing over here is really this like non-linearity, okay? Non-linearity. And so as a secondary example of how to do this, we're going to take a field trip of the mind right now, and I'm going to use a big nonlinear class example. And we're going to imagine a test that a school has derived to determine whether or not it is a senior skip day, okay? Is today a senior skip day? So what we're going to do is we're just going to pull the fire alarm, and we're going to see how many people leave by the door over by the athletic trainer's office. And in theory, we should be able to look at the number of people coming out of the door at the athletic trainer's office and determine whether or not it's a senior skip day. That's the goal of this thing, okay? Can we do this? So we have a big problem. How do we figure this out? So let's say that we've got all these classes on hand over here, right? Class 1, class 2. I don't really love. I think I'm hitting a button that I shouldn't be hitting. I think that's why this is happening, and it's actually driving me bananas because it was happening in the other class. I need a different stylus. So let's say I have some classes over here, class 1, class 2, class 3, and these classes are all going to dump out into hallways. Let's say we've got our AI class up here. Let's say we've got the cafeteria, all these different classes, Mr. Tra's room, Mr. Rose, whatever. And let's say that these individual classes are going to go channel themselves down into a few different hallways over here. So we've got the way that these people can meet their different hallways. And, I've got these different hallways over here, and maybe they can go upstairs, and maybe these guys will go upstairs through that hallway over here, and then maybe they'll come back down over by the gym. And finally, they're going to kind of work their way out by the that final door over by the athletic trainer's office. Okay? So we've got this network where we're going to pull the alarm. We're going to have everybody try to leave the building, and we're going to construct the school in such a way that we're going to get output at that door on a senior skip day, right? So we're not actually changing our data. What we're doing is we're changing some transformation. I'm not changing the fact of whether or not today is a senior skip day. I'm not changing that. I have my class of students in the building. I know who's here, who's not here. And maybe it is, and maybe it isn't. But what I want to do is I want to tune the way that these halls are constructed. I want to tune my weights across and throughout the school. I want to tune the obstructions. I want to tune those decisions throughout the school that are going to guide people out that door when it is a senior skip day. And I want to guide them not out that door when it is not a senior skip day. Okay? To do that, I have my inputs, I have my scores, I have my grades on my tests. And the way that people are going to flow together and the way these grades and the influence is going to become really a not like linearly separable mess at some point, right? When I'm looking down by the foreign language hallway, I don't know where these individual students have come from or haven't come from, but I do know what I can control inside of here, right? So in the same sense that I don't know what the scores the students are getting on the test, I do know how I'm going to weight this hallway. I do know how I'm going to guide them through that hallway. I do know that maybe I can put a conveyor belt inside these hallways, right? So kind of like the airport, I'm going to start loading this place up. I don't know that I did the best. Oh yeah, this guy also has a network connection over here, and this one is going to have. So yeah, so I do know that I'm going to start putting conveyor belts inside of these things, and with my conveyor belts over here, I have some weight and I have some weight on this guy. So I've got conveyor belts, and I'm going to use these conveyor belts to control the flow of people going through there or not going through there. Okay. And this is for the sole purpose of shuffling people out when there's a skip day going on. And I also have conveyor belts, and maybe I need to slow them down. Maybe I need to just like throw rocks in the hallway, right? So I could also put lots of rocks over here to maybe make this one a little bit, but that's still some weighting. That's still some scaling to the amount of people that are going to be actually moving through there. So the weight functions, in order to figure out the weight function of how this influences it, it's still that same basic problem, right? I should be able to, I know what my rate of change that I've established for this hallway is, so I don't really care what you're getting on the test. I don't really care how many people are going through there. I know the rate that I'm going to be flushing them through there. And what I want to do is I want to adjust these conveyor belts. I want to adjust my obstructions. I want to adjust the scales on the tests in such a way that when there is a senior skip day going on, I'm getting people coming out of this one, and otherwise I'm not getting people coming out. All right. So in order to do this, we're going to have some like gating functions going on over here, right? So I could have it so that I choose to either not let people go through at some point, and then I choose to do let people go through. Kind of like a one-way valve. So if we think of intersections where these hallways are coming together, it's entirely possible that I could stage teachers or staff or somebody. Let's get people out there. So this is a grand experiment to determine if it's a senior skip day. We're going to pull the fire alarm. We're going to set conveyor belts all around the school for this. And I'm going to have people standing at every single intersection that allow for only flow in one particular direction, right? They're not going to influence, they're not going to change how fast they're going. They're just going to kind of say yes or no, right? If you want to go that way, nope, sorry, you got to go that way. Can't do it. We're all going that way. This becomes that ReLU function. This is our ReLU function. As those people are channeling through here, I've got somebody saying either no or yes. He does not influence their speed. Their speed is determined by that volume that's coming through, but he can sit there as a no or yes on this thing. But there may be some bias that this individual has as well, right? So he could have some attitude. Like if you're kind of stumbling around, at some point, he kind of allows you to go through and keep moving. But if you're below some other things, so the bias is that decision tree where it sort of allows you to go through. Like it's making some kind of subjective opinion of what is actually allowed to go through this. So, that point can be shifted. So we've got these things going on over here. And the influence of allowing some and not others to go through is going to introduce nonlinearity into this collected mess, right? So if I've got somebody sitting at the base of the ramp and telling everybody they have to go that way, that's going to introduce a nonlinearity to the system that wouldn't otherwise just be like linearly separable out. So we've got some nonlinearity inside of there. But we know what that derivative is on this thing. We know its decision tree. And because we know its decision tree, we're able to mathematically piece this thing back the same way that we could piece back your individual grades influence on your GPA. We just need to know the derivative and multiply back the derivatives to that little piece. That's basically what it is. That's But there's a little bit more, but essentially that's what it is, right? The influence of this guy is going to do that. And so in a sense, by being more restrictive or less restrictive, or by making a little conveyor belt that moves people here, like that really, so I've got my people mover, right? So by having my people mover and adjusting that people mover's speed and flow rate, I can effectively change how much people are coming out over here, because I know that this is going to have ripple effects that go down, and that ripple effect is going to be experienced here and here. And the same story over here. By putting a conveyor belt out on the ramp, I'm going to influence how many people are going down the ramp, and that will have some influence, albeit tiny. It will have we can figure out how that is going to influence the final output of going out that door. And our goal in constructing all of this together, again, is to have it so you're either not coming in, and by 0 people coming out, we can say not a single skip day, and then as it goes up, we're going to say more, and it becomes a yes to a single skip day. Yes or no? Is this kind of sort of making any sense here, or maybe? I don't know. I feel like I'm just throwing out weird amounts. So here's the deal, though. As this thing exists and lives, what we've also got over here is our final activation is our friend, the sigmoid, right? Our final activation is the sigmoid. And so we can control effectively the stickiness of the sigmoid, so to speak, right? We can take the, do you know what a turnstile, do you guys know a turnstile? Like the thing that you walk through, like the little ticket, and it only goes in one direction, like when you're getting on the subway or something like that. So the turnstile is going to be my sigmoid function. There's only one way through this thing. It's either 0, like you can't go backwards. It's got to be 0 or 1. You got to send people out through the sigmoid over here. But I could like adjust the tension of this turnstile. I don't know if you've ever been through like really sticky, I don't know, to like fight your way through this thing, right? So I can control that sort of response to this. I can control my sigmoid, but he has a known behavior that's going on. So I'm going to control the flow. I've got my sigmoid over here. And I know that the amount of force that's going to be sort of driving people through the turnstile will determine the output, right? If there's not a lot of force coming over here, then that's basically going to be 0. But the more force, you could sort of envision a lot of people coming out as a mental analogy over here. So the deal with the sigmoid is this. The derivative, the rate of change through which I can squeeze people through this turnstile, is kind of dependent upon how many people are like waiting behind the turnstile. I don't know that this is the best analogy, but in the sigmoid, the derivative of the sigmoid is not linear, right? As you get up to much higher functions, that derivative is really tapering off and it's close to 0. It's not just 1 like it was with our GPA grading scale. It's not always 1. You can't just multiply that through. The derivative of that sigmoid function actually kind of depends upon the input to that sigmoid function. And if my input is really low or negative, it's going to have a different rate of change on the output. The example that we used earlier is if you were selling answers to a Math 5 exam, right? The rate of change of the collective opinion about you is actually going to be far less. You're not going to have a huge change. Like if this is your 10th Math 5 exam that you've sold answers for, like that's not really going to change people's opinion. But you could imagine if this is your first Math 5 that you ever sold an exam, that's going to have, so the rate of change is dependent upon the input. It's not just the output. And so in that sense, when we've got this highly interconnected network over here, I cannot treat this ramp in isolation. I can't just be like, I actually need to know. So this is the sort of like the magic of partial derivatives in the chain rule, right? We do the chain rule and we're like, oh, you take this and this is the partial derivative with respect to this, and this is the weight with respect to the output. Great. But he does not live in a vacuum. That does not live in a vacuum. That partial derivative exists because of all the other partial derivatives. They all have to work together. And it's the input space and that collective input space mapping that's going to define the input. So as much as I could say, well, I know that, a small change over here is going to cause a change of a little bit over here. Well, that same small change over here could also cause a huge change if everybody else is not triggering. Does that make sense? Like the amount that I adjust this conveyor belt, is going to influence the change of this guy different depending upon what all these other inputs are. Do you agree or disagree with that statement? I've got some nods. Do you want me to say that again? Yes. I'm going to adjust this conveyor belt at the base of the ramp. And that's going to cause some change in the output. My goal is to get the right value of this that triggers the output to what I expect it to, right? And I can mathematically kind of figure this out. Like, I can figure out what the formula of how a change over here is going to cause a change over there. But that doesn't really help us without knowing the input as well. I also needed to know the input. Yeah.
The input's like the number of students in each classroom.
Yeah, the inputs are the number of students in each classroom. Yes. The inputs are the number of students in each classroom. And the number of students in each classroom is going to be different whether or not it's a senior skip day. Okay. Some senior skip day, it's going to be different. But on any given day, the number of students in the classroom could be different as well. And so I know that changing this is going to cause a change in the output, but I don't know how much change. I can mathematically figure out how much. I can multiply back my chain rule over here to figure out the individual parts to see how much influence you're going to have. But in the end, the amount that this is actually going to change the final output is ultimately dependent upon feeding inputs to everybody else over here, because I'm going to need to know what these other guys also are doing to do this. And so the way we're going to figure out how much change this has in the overall output and how much influence he has, because we're going to try to match to our data, is we're going to run a series of little tournaments. We're going to run the tournaments because it's too much of an inconvenience to send the entire school out every single time. So what we're going to do is we've got our big constructed systems of turnstiles and people guarding doors and whatever like that and directing flow over here. We're going to pull the fire alarm and we're going to have only select students walk out the door. And that's going to put some different subset of numbers over here. And that different subset of numbers is going to allow us to kind of see, oh, it's going to basically allow us to find data points on the input-output mapping space. Yes.
But this, if we only use like a little bit of those students, right?
Yeah.
We're not gonna get 100% accurate.
Yeah. That's a good observation. So when you think of finding minimum, so for the benefit of the group, when you only use a little bit of students, you're not going to be 100% accurate. I want you to hold that thought, because that is like a crucial thought for understanding. Continue.
And if we apply this analogy in terms of like training on like a data, right?
Yeah.
The iris data set, right?
Yes.
Does that mean like instead of taking the entire data set, we take just like one or two? Then
30, 20. Yeah. So we're taking 20 of the iris data set. We're not taking the whole data set. We're taking 20 at a time. We're taking 15 at a time. 15 here, 15 there, 15 here. Now, oh, continue. Yes. Say that again. random sample. We're gonna take a random sample. Okay, but we know that there's this nonlinear thing and different parts influence different ways. So we're gonna take some random sample. The volume, the fact that we don't have full volume coming over here, maybe it's like random. Maybe what we really need to do is run random senior skip days. So we have full volume, but whatever. We can figure this thing out. The point is that it's not like it's different than what we're used to in a pure mathematical sense, right? When you have the curve and you're like, where's the bottom of this curve in 3 dimensions? You take this slice, you take this thing, and it's very neat and tidy, and you work your way down. It's not like the hiker who's like carefully stepping down and calculating or like the water that's going down the exact natural gradient all the way down these things. We're playing guesswork over here. We're like, oh, okay, I took this step. That seems to be, oh, we kind of stumbled over here and we kind of went in there. And what we do is when we figure out sort of from that sample, we're like, okay, from the sample, this seems to be the derivative over here. It might not actually be accurate, but what we're going to do is we're going to try to tune in the direction of that derivative, which may be kind of right given the mean of all of these values that we put in there. It's a messy stumble down a mountain that goes back up the mountain as well. It's like my dog looking for his ball on the side of the mountain. He will work his way down, but it's not like he doesn't run straight down. Like he'll stumble up and get caught on things and sniff and go back up to eat something. So we can separate these guys out, and we'll separate them out. And the way to separate them out is through these things called the partial derivatives, right? And so what we've got over here are these guys over here, right? So if I've got some input over here, and now to start doing the mathiness of this, I'm sorry, going into math. But we've got these inputs and we've got these outputs. And so the problem in like the simple sense, kind of like what I had with my grade scores, these things are just going to need to scale. And you'll be like, oh, it's not one. And we don't really need to calculate a whole ton of nonlinear stuff because we just need to, let's do nomenclature. Ooh, wow. Nomenclature. So as far as nomenclature is concerned, we have inputs, we have weights. I like to introduce this superscript. I saw this, there's a video that does this as well, and you'll see this from time to time. Many people will do this way. This is my layer number. This is my output. My layer is the sum of all these inputs. It's the weighted sum, the weighted biased sum, right? And then it runs that weighted biased sum through a transformation function. That weighted biased sum is weight 0 times input 0 plus bias 0. That weighted sum is called Z. And the output of any network is generally considered to be like, if you're using a sigmoid, it would be sigmoid of Z. So there are 2 things inside of here, right? So in order to figure out the weight of this input with respect to the output, the weight is influenced, the overall score, and that derivative would be influenced by everything going on inside this node, right? By the weights. Not really biases, because those are going to differentiate right out. But it is going to be influenced by the derivative of that activation function. So we need to know the derivative of the activation function and the derivative of this Z with respect to how it changes not the input, but how we change with respect to the weight, right? How changing the weight changes the output. How does change the weight change the output? We don't really have control over the inputs. We're going to have to empirically figure out based off of our inputs. But how does changing the weights change the value of the outputs? We're given inputs. We're just going to be given a handful of numbers. We don't have control over the handful of numbers that have been given to us. I don't have control over my students who have or have not decided to skip today. So what this looks like is, where did I do this? So this is where I'm saying like kind of light. the derivative of sigma with respect to z. I'll leave it to you guys to do this. It's the sigma of z times 1 minus sigma of z. So one of the reasons that we use the sigma as an activation function is because the derivative of it is actually kind of like not that hard to figure out. So I've got this derivative, and if I know that derivative, I know how this how this output is going to change with respect to the input. And it's going to be different for different values of the input. Low value, you're going to get one derivative. High value, you're going to get higher derivative. And we're going to take this notion, we're just going to play it all the way back, right? So if I use some weighted input over here, that what I'm going to ask you guys, we can step through this next class. We got to go to lunch and do things like that. But this kind of extends right through the ReLU has a less complicated derivative. He has a fairly straightforward derivative. And the chain rule is going to be this thing that allows us to activate these individual things. And so we begin to ask the question of here's my z, how do I figure out the change in sigma with respect to W0? How do I figure out the change in my output with respect to this grade? How do I figure out this change of my grade with respect to this weirdly scaled test and this weirdly scaled test? And so I'm not asking to get a new grade on this thing. I'm asking the teacher to change the curve over here. That's what we're doing. We're looking to change the weighting function. And what you would want to do is we can mathematically figure out this, but it doesn't live in isolation. I need to stop. We'll pick this up tomorrow and we'll do some problems. And I don't know if this hopefully made some sense.